is then expressed as in this formula, the G are to 2G minus 2 and G are square to n to the power of h, where G is the genus of the surface obtained in this way, and h is the number of the loops in the original diagram. The full perturbation theory amplitude is then expressed as the sum of a genus of gross Riemann surface, where each sum f of G depends on the two-loop coupling. The conjecture then is this, that the closed string theory whose zero amplitude is given by f of G. In this case, the two-loop coupling T is some parameter of the worldsheet theory, and in known examples, it is typically a geometric modular of the target space. In field theory, variety of game theory can be realized as relatively effective theory of open string on D-branes. The second graph of this game theory has natural interpretation as describing open string world sheets ending on the D-branes. In this context, the two-loop conjecture has a natural generalization about the conjecture between D-branes and closed string background. Let me explain what I mean. Consider this open string diagram with fixed number of handles and holes. It is weighted by the factor lambda is the string coupling constant, to 2G minus 2, and n lambda to the h, where the factor n here comes from the translation factor for each hole. If we take the lower degree of this, we obtain the game theory amplitude for the corresponding ribbon graph. But this is simply a kinematical fact about Rho limit and has nothing to do with the conjecture by itself. In fact, we may choose not to take the Rho limit, and we can still make a conjecture. The conjecture is that after summing over a number of holes here, for a fixed number of handles G, we obtain G with closed string amplitude. On this closed string side, the two-loop coupling T is some parameter of the closed string background. So, as I have written here, we can make a more general conjecture about the equivalence of the D-brane and closed string background, and this is the implicit here that I will explain the large integral. And so this is the limit of the closed string side here, and the limit of the closed string side. This generalized conjecture reduces to the traditional conjecture about the large duality. Now, by now, several examples of large M duality have been discovered, assuming various M-series dualities and the equivalence between D-branes and closed string background. The ADS-CFT correspondence is a well-known example of this. Now, another interesting class of duality is the equivalence between topological open string and topological closed string, which I call here topological string duality. The first type of topological string duality discovered by Gotakuma and Buffer states that the Chern-Simons gauge theory in 3 dimensions is equivalent to topological closed string with 8 twists on the Calabi-Yau threefold. In the spirit of the previous transparency, the Chern-Simons gauge theory can be kinematically obtained from topological open string on A-type D-branes resting on a deformed Calabi-Yau singularity, and this was shown by Witten. On the other hand, the corresponding closed string is living on a small resolution of the same Calabi-Yau singularity. So the equivalence is between open string on D-branes on the deformed Calabi-Yau singularity and closed string on the resolved Calabi-Yau. Very recently, the Miller version of this duality was investigated by Digraph and Buffer. Here, the topological string in question is of the B-type, and the role of the deformed Calabi-Yau and resolved Calabi-Yau are exchanged. Namely, it is an equivalence between open string on D-branes on the resolved Calabi-Yau and closed string on the deformed Calabi-Yau. In the closed string in this case is known as the Kodaira-Spencer theory of gravity. So the amazing thing about this is the open string side gives a matrix model of the type studied in the context of serious one string theory in the early 1990s, but we do not